So Shomajit is a doctoral researcher at Shanghai Jiangtong University. His focus is basically on AI for science and computational fluid dynamics. He has done his master's in data science and AI at University College Cork, Ireland. And he then worked as an assistant researcher almost for 2 years at UCC and Trinity College Dublin in LLM modeling for geospatial analytics. He has done his bachelor's at Techno India University in CSE. Today, we are very obliged to have him as our speaker. Over to you, Shomajit. You may start your presentation.
Yeah. Thanks, Anvesha, for the introduction. Just as she said, I'm a doctoral researcher at Shanghai Jiaotong University in China, and today I'll be presenting on behalf of my colleague at IIT Varanasi, our latest publication in sustainability engineering for wind power density modeling and maintenance driven digital surrogate for windmill designs. So let me share my screen. Just a second. Can you tell me if my screen is visible?
Yeah, it's visible.
Yes, it is.
Yes, so the main topic is AI calibrated framework for adaptive maintenance of wind turbines. And that is our main areas of research, primarily wind turbines and wind farms. So so the main motivation of our research is there are a lot of wind farms in India, especially in the coastal regions, as well as some in the northeast regions and in the subtropical region around the South India. So these wind farms, due to intense weather conditions in India, especially during the summers and also during the monsoon, the wind farms suffer quite a lot of damage, and we want to model how what's the window of doing maintenance and running maintenance in this kind of in this kind of severe weather situations. So there are problems on modeling this kind of this kind of situations. The main problem is weather. Weather is ever changing, and it's very difficult to model. There are various models, various weather models out there which can predict weather very good, but they are not always reliable, because for maintenance you need to have instantaneous decision making rather than long-term decision making. Weather prediction models are very good for long-term prediction making, but they're not very good for instantaneous decision making. Another problem is most studies focus on wind speed and annual energy productions and power densities, but they completely ignore the maintenance planning needs. What are the actual needs? What time frame to use? Which maintenance equipment should be used in certain weather conditions? Another problem is AI calibrated frameworks that are out there. They don't actually provide a risk aware maintenance scheduling. Instead, they provide a deterministic way of thinking where, okay, these are the variables and these are the outputs, and this is what I'm these are the optimal conditions you need to have. But that's not always the case. We need to have risk analysis. We need to have uncertainty analysis that in order to make effective judgment during the maintenance sessions. So the main objective of the study is to propose an AI-enabled data-driven framework for adaptive wind turbine maintenance using long-term hourly IMD observations at 6 different sites. The sites are chosen based on their location, 2 inland and mostly coastal, because our main target is coastal regions. These areas get affected by the by the severe climatic conditions more than the inland regions. The inland regions mostly suffer from heat, whereas coastal regions suffer from monsoon, heat, as well as tidal waves. So in our data set that we worked on, it was provided to us by Meteorological Survey of India and organizations working in Indian government for climate modeling. The problem with this data set is it's quite intense, quite huge, and often very messy to deal with because it's higher dimensional and it's multimodal. So there is lot of dense embeddings, or what in another way to say, dense information that contains within this data set. Now, these locations we observe over a period of 38 years, and we get hourly data. We have hourly data, so you can imagine 38 years of hourly data. It's quite huge, and we have some fixed heights at which. So before, just for context, every windmill has a certain height, which we call it the hub height. So now this height, we have the data at 10-meter height, but sometimes heights change. There's 100 meters of height, there is 50 meters of height. So sometimes there are different heights that we need to observe. Then there is a 5.3% of missing data. Now, it might seem 5.3% not very much, but when you consider the size of the data, it's huge. And that this 5% makes a lot of difference in analysis. Oh, it's not changing? Oh, maybe it's because of the full screen move. Is it now visible?
Yes. Can you make it a slideshow so that everyone can see the?
Yeah. I'm turning it into slideshow, but let me see if is it moving now? If I'm changing the slides, is it visible?
No, it is not moving. It's in study sites and data overview.
Oh, okay. Okay, I know. Okay, I'll just change the slides to full screen as I move forward.
Okay, sure.
So yeah, so if you can see this slide, study sites and data overview, it shows you the overview of our data set, as I discussed. So we consider pre-monsoon seasons, which is summer season, and monsoon seasons, which are our peak seasons for maintenance, because this is the season where we need a lot of maintenance and instantaneous maintenance, not just long-term maintenance, instantaneous maintenance, because the hubs get damaged pretty easily. So this is another purpose of this study, is to model these hubs so that they can sustain long-term damage, but also sustain instantaneous damage, and we can do quick instant decision making. And this 95, the ramp P95 is at 95 quartile ramp speed. So it's basically the movement of the rotational movement of the rotational effect of the wind speed on the hub or the windmill. Now, yeah, so and we measure the WPD, which is the annual mean wind power density. So it's how much power does the wind speed have an effect on the hub. And we see Tuticorin report the highest wind power density because it's in a coastal region and it's in the southeast coast, and you can see the southeast trade winds bring a lot of heavy monsoon during the monsoon season. We can see the lowest record at Jaipur, which is in inland. It's, of course, as it turns out, in Rajasthan has recorded over the least powered wind because it's quite arid. So yeah, so this is the range of our data set that we are working on. Okay, so now let's talk about the framework that we are using, the methodology that we are using to analyze this data and to get actionable insights for our modeling. First is quality control. As I told you before, the data set is ranged. It's ranged pretty big, and it's very high dimensional. And at the same time, there's missing data, which might not seem much, but in a large data set, it makes a lot of difference. And so we kind of do a little bit of QC, which is quality control. So we understand outliers in the data set. We understand we need to scale the data set to different conversions, different units across 6 sites, because they are not uniform, because different site stations may report the data in a different way. So we don't have always the uniform units across all the different fields. So we need to unify them, fix outliers, clean it as much as possible, and prepare the data set to our need. Then we need to study heat maps, where we not only study temperature, we study climatology, diurnal climatology, seasonal variations. We study monthly variations, hourly variations. And as you can see, here's the formula for calculating the WPD, which is a density function, where you, with the velocity, is half of the velocity cubed to multiplied upon the density of the wind at a particular time. So you see there are a lot of scaling going on and a lot of hourly and seasonal analysis that needs to be done. And then we move to a volatility analysis. So what is a volatility analysis? It's an hour-to-hour mapping. So what we want to see is at different quartiles. So you have different quartiles, the first quartile, second quartile, third, fourth. So you have different quartiles. What's the change of WPD? So this is kind of like a volatility analysis that needs to be done for a time series data. And then we move to the maintenance windows, where in order to make our model as much as reliable, we do bootstrapping as well as different kind of cross validations to make sure that our models don't overfit. And we create windows which are 6 hours, because maintenance times are 6 hours usually, roughly. There is no fixed time for that, but usually we consider 6 hours based on past records, and as we discuss this with the employees or maintenance employees. And we create a deterministic window. In this deterministic window, we kind of measure risk patterns. So what are the risks? What are the risks associated? Like if I go in today, if I go in this 6 hour window in this time period, and I try to do maintenance, what kind of problems I might face based on climate, based on the hub status. So hub status is monitored instantaneously at every site using sensors. There are different sensors within the hubs, and we measure this data instantaneously at every site. And based on the data, we can know, like, if the hub is functioning properly, or if there is a leakage, if there is a electric discharge. So from that, we kind of able to translate that data into our model and generate a POK. So it's like a threshold where we see, oh, okay, it's a very straightforward name, POK. Like you can, it's okay to go for maintenance, or it's not okay to go for maintenance if the threshold is within less than 70. So this is a risk threshold, not a. So the lower the value, better. Then there is regimes. We also do dimensionality reduction across to understand these regimes and extremes in the weather multimodal in the multimodal weather data. Now this whole thing, we put this into an MCP based framework where there are LLM models doing decision making at every stages. So first stage, second stage, third stage. As new data is introduced into the model, the LLM models kind of reason where to send this data, which part of the analysis we should send the data. If there is no missing data, so there is no need for doing missing analysis. There is no need for outlier analysis. So this kind of system where there is an MCP autopilot doing real-time decision making helps progress towards a much more faster pipeline. in terms of machine learning and in terms of model building. It improves the speed of the platform as well. We call it WindOps Sentinel. Sorry for the catchy names, but the WindOps Sentinel. Now the month hour. So let's talk a little bit about the climatology. Yeah, let's talk a little bit about the climatology. So 3 main patterns has been observed from our analysis. One is the coastal peak energy. So as you know, as we see, Tuticorin experiences very heavy monsoons, but it's also because of the tidal energy. And then there is a huge spike at Mormugao and Madras as well, where we see 150 to 300 wind power density, which are almost criteria for cyclonic winds. Then there is diurnal patterns. We see from midday to late afternoon and early morning hours, there is a huge variation in site data. So we observe these patterns, and it's very interesting to observe these patterns and make further judgment calls and further analysis on these kind of like coastal peak energy, diurnal patterns, and monsoon dominance. So these are the monsoon peak ranges that come out from the analysis. So the interesting thing about this and this particular aspect of the result is we were trying to model hub data. We were trying to model the results for wind speed farms. We were trying to do modeling for wind speed, and we were trying to model for windmill farms. But as a side product, we got to model climate in India. So this is the beauty of analysis. When you try to do something, but you get something else as a side product, and that's might be more useful. So we are currently working on another climate model, which we will publish soon. Okay, now this is a little bit about the volatility and ramp rate analysis that we got at different quartiles. We see 95% is selected for volatility metric, but why the 95%? Because it gives us the best way to it gives us the best range of data for doing this kind of analysis. And the key finding is we see higher mean WPD correlates strongly with the greater ramp volatility. So what it actually essentially means is when there is high, which is it's very basic to understand, where there is high density of wind, the ramp volatility or the risk associated with the ramp or the system increases, especially in the coastal sites where high energy potential with short intense variability happens. So the maintenance window shrinks a lot. So there is very few maintenance window, like maybe for one to 2 hours maintenance window for certain cases, probably early in the morning when there is less variation in wind due to temperature drop. So another observation we come across is operational insight, where best maintenance windows occur during periods of LOW, which is low ramp volatility, and low WPD during the post-monsoon or these winter seasons. So winter is said to be the best season for doing this kind of maintenance, but this is long-term prediction. It's not short-term prediction. Now, how do we optimize the maintenance windows? There are two complementary strategies. One is the deterministic policy. It's very it's statistical in nature. Fixed 6-hour window. We get the WPD. We have different fields, hours, and we do bootstrapping. We do we have a threshold. We generate the threshold. We do that, and then there is risk control. So which is uncertainty modeling. We introduce these metrics like POK, Paolo, which gives us the 20th percentile of different 6-hour windows and fallbacks on where to go back if we don't have a particular window. Then we also conduct a little bit of sensitivity analysis, which basically gives us thresholds for the confidence intervals or thresholds for different duration that we get. Feasible sites, which is the best months for doing this kind of maintenance. For Madras, as it turns out, is January and February and March. And Tuticorin is April, and Ahmedabad it's November. So different sites have different site windows. So this is completely novel to this application. There hasn't been any model anywhere that actually can predict these exact months of sites based on uncertainty and based on different parameters. This is a brief outlook on all the sites, the best maintenance result across all sites at different hours, at start hour, 1 hour, 5 hours, how many hours it's needed for doing the maintenance, and which are feasible, which are fallback. Yeah. So fallback sites are more. So for example, if we have a grid of these kind of wind farms, if we maintain 1 or 2 wind farms, what are the fallbacks? If we are not unable to maintain one wind farm, what are the fallbacks if to neighboring wind farms if we can maintain them, and it still will be as effective in generating electricity for local population? Yeah. Finally, we do a little bit of clustering and embedding studies because we have a lot of data, so we can actually find different high wind, low wind situations or optimal clusters based on different patterns on the wind data. So this is mostly climate modeling instead of maintenance. But this is very important because from this, there are various patterns that emerge, and we feed these patterns back to the model, which is very good for reinforcement to the model. Yeah, so these are the C1, C2s. These are different levels or percentages of dominance of high wind speed and low wind speed. And there are 3 main techniques that we do for dimensionality reduction. One is PCA, UMAP, and TISNI. These are very well established. PCA captures linear structures like gradients very good, whereas for nonlinear embedding, like separation between clusters and wind patterns, UMAP is very good. And for local structure, for example, color coding of different seasonal based clusters, that's very good for TISNI. Yeah. And this is the POT GPD analysis, which basically Pareto distribution. You kind of do that and peak threshold analysis. We kind of do that for finding key points regarding each key maintenance points regarding each stations, where 50-year return level. So like after 50 years, there is reportedly exact same climatic situations happening at every intervals or even distributions at roughly 50 years in terms of climatic conditions. And we see coastal sites show large extremes, which is to be predicted, and inland regions like Ahmedabad and Jaipur remain normal level. Whereas monsoon and pre-monsoon seasons are the worst because of heat and rain. And finally, let's talk about our platform, WindUp Sentinel, AI calibrated web platform. So this is a digital surrogate. Now, digital surrogates are very useful for modeling this kind of weather phenomenon and also machinery systems in industry, as well as realistic machinery systems for power grids. But the main problem is how do we introduce AI into the system and calibrate them? AI is not always reliable. Now, one might ask, why would we use k-means, or why would we use machine learning techniques instead of deep learning techniques? Deep learnings are black boxes. There is no guarantee result or there is no transparency into the models. There is no guarantee that these results will be reliable. See, deep learning models mostly work based on probability, and the more biasness you add into the model, the more biasness will be there in the result. But instead of machine learning, which is statistical in nature, we have a very strict regime to follow, a strict pipeline to follow and get results. So as it turns out, statistics still is the most important tool, even in the age of LLMs and high-end deep learning models. So this is a basic pipeline. We build the front end using React. We build the back end using Node and Python. And the analytics engine is basically a statistical engine and AI modules, so like k-means and UMAP and clustering and are used. Now, the only part where we actually use high-end AI modules or LLMs are for decision making. Which tools to pick when? That is very good area under which AI models like LLMs can perform, not for scientific discovery at the moment. So now the platform validation we have is from the platform validation we got annual mean identical to the actual study. So the platform is actually giving us very close result to the actual experimental study, with very minute tau differences due to pre-processing and rounding, because still LLM is not that smart. It still will have errors, even with fine tuning and even with RAG or whatever models, whatever techniques we could use to inform the LLMs better. And the key conclusions to conclude, we see this study is a very important first-time study in the field of power grid development as well as wind power maintenance in India. We have attracted quite a lot of attention globally in this research, and we are also conducting more experiments in climatology as well as computational fluid dynamics, in using computational fluid dynamics to model climatology, as well as developing smart power grid systems, and adding more and more LLM-based reasoning into this, but keeping statistics at some point. Now, the main thing, this I have already talked about, so I'm not going to repeat these results, but this is the main conclusion, that the platforms are working very good, and we are getting very good results. But at the same time, there are open problems that need to be addressed, like LLM-based reasoning. How do we develop more climate-based reasoning? How to make it more smarter? How to make these models move away from the deterministic models to add variations, to add instantaneous, much more instantaneous uncertainty into these statistical models. We do need probability to some extent. When do we know to sacrifice biasness to definite deterministic results? What are the scales? When do we decide? So these are some things that need to be asked, and some need to be explored in further studies that we plan to do. So thank you, everyone, for this session. I hope this was an interesting session, and you have some interesting questions that you need to ask. So as I said, this is our funding. This is our funding call from Indian Meteorological Department, and the study is supported by Government of India. So thanks, and I also thank Harendra Kumar, Dr. Harendra Kumar Yadav, for developing this presentation and developing this and spearheading this project. Thanks. If you have any questions.
Thank you, Shomjit, for this great talk. Now I'll be requesting everyone who has any question to ask him one by one. We can continue the question and answer session if anybody has any question. Anybody has any question regarding the presentation?
Anisha, please check if there is any question in the chat box as well.
Yes, ma'am. No, I can't find any question in the chat box. There is no question in the chat box. I don't think anybody has any question, ma'am.
Okay. So either everything is understood or nothing is understood. So students, we are requesting you, if you have understood, it's great. If you don't understood anything and you just don't want to make yourself asking
I would be
question,
interested. Yeah, I would be interested to know what you have. Like, I always interested to interact with you, everyone, and see if you have any insights what you want to contribute to the project. If that is also a question,
one
that is
question
also
is
great.
there.
Yes.
Anisha, just check. Yeah.
Sharkar. So his question is, what are the factors on which windmill life depends?
So yeah, this is a good question. There are a lot of factors. Mainly you can divide them into two main factors: external and internal factors. External factors are like climate that we are trying to model, and there are other factors instead of climate is also location, latitudes, longitudes, height, basically above sea level or how much above sea level. And then there is the internal factors, which are circuitry, electronics within the hub, how they perform. So in a digital twin, we try to simulate them in a computational model where we have external factors, we have internal factors, and we try to collect data using sensors. Climate data are also collected using sensors and other weather balloons or various different equipments in the lab for weather modeling across different stations. So this is how we get our data. Yes. Internal factors are considered as well in this in this study. So we have a digital twin already. This is a software where for across these hubs that we have taken in the study, like Ahmedabad, Tuticorin, we have some windmills and we have their sensor data. So we also add that to the pipeline to get the best possible results, because you can't consider only external results to generate maintenance windows, because we are maintaining the machine and we need to know what's going on inside it. Yeah, so that's a very good question. Most digital twins require validations. And so in terms of engineering, if you are familiar with I think if anyone here is from different engineering domain, for like mechanical or chemical, they will know that there is not in any situation where simulation will be same as the machine itself, because simulations are derived from ideal conditions and machines are not ideal. There is a difference. And there can be instantaneous error at many times, and sensors may be faulty. So yes, validation is needed. We have a certain cases where we validate some of the data, but that is a challenge at the moment, that we can't get exact what is happening in the machine all the time, or exact whether at that moment all the time. This is a limitation. This is a physical limitation. Thanks for the questions. Very good questions.
Do you have any other question from anybody else?
Yeah, so I wanted to know whether is there any measures to safeguard the data. I mean, that's we are collecting from that particular technology. I mean, today we know data is a very powerful asset. I mean, utilizing that, some another country can uh, misuse that against our energy sector or something. I mean, we have seen in fact, like it has been misused. I mean, what's your take on that?
This is a very sensitive topic, but yeah. So safeguard rails are always good to install in any kind of AI systems, as well as any digital systems, because without security, there could be data leakage, there could be hacks, there could be nightmares, especially when a power grid is concerned, modeling power grid is concerned. But the main thing that we are doing is we don't publish the data itself. The data is not readily available because this data is only available to the concerning researchers with security clearances. If you have no security clearances, you can't work on this field. So you have security clearances and then you work on this field, but and it's only restricted to those people who are dealing with the data. But at the same time, there are security measures installed within the Sentinel Ops system. At the moment, it is a proof of concept and it's not a fully developed system. So we are working on to make it a fully developed system. As it progresses, we will transfer this to Government of India, and they will. I hope they will have much more secure system in place to maintain the security of the data. And for publications, we are not using the whole data for publications. We are only presenting the methodology and the results that we are getting.
Okay, thank you. Thank you.
Do we have any other question? Is anybody else wants to ask any question? I don't think so. Anybody want to ask any question? Fair enough. Thank you, Shomajit, for this talk. We are obliged that you gave this speech. Thank you. Today we will be ending our session here only. Thank you,
Thanks so
everyone,
much.
for participating. Thank you, everyone, for participating in this session. And we will be requesting everyone to fill the feedback form, which will be given afterwards. Thank you. You all can leave now.